Think of the standard identity provider model currently operating across global networks as a monolith. We rely on a few massive, centralized servers to verify who we are every time we log in or make a transaction. To engineer a decentralized system, we must shatter that structure completely. The core security vulnerability of the current model is possession. Central authorities must physically hold and store your private data on their servers in order to verify your identity against it. Our engineering objective is to build a sovereign identity layer. This requires designing a system that verifies user attributes while granting those users direct control over their own data. Achieving a persistent, user-controlled identifier requires that we move away from centralized servers in favor of a trustless, decentralized protocol. To build this, we rely on a blueprint for a two-tiered architecture. Decentralized verification requires splitting the protocol into two distinct environments. The top tier handles surface area network orchestration. For this, we utilize TypeScript, which is natively equipped to interact with standard web architecture. The bottom tier processes the cryptographic core. Here, we utilize Rust, taking advantage of its strict hardware-level execution to manage sensitive mathematical operations. The space separating this network layer from the cryptographic engine is known as the cryptographic gap. It represents a critical vulnerability zone where data is passed between public routing and private computation. Securely traversing this specific gap requires the creation of entirely new credential objects, designed to carry encrypted proof across the boundary without exposing the underlying data. By strictly isolating the web orchestration layer from the mathematical cryptographic layer, we create the structural foundation necessary for a sovereign protocol. We start at the top, at the network interface layer. This is where autonomous user nodes actually interact with the broader internet to initiate requests. To route identity claims without a central database, the protocol uses decentralized identifiers, or DIDs. These are dynamic, user-controlled strings of code that point to specific verification endpoints. TypeScript optimally handles these JSON-formatted DID documents. Within this environment, geometric DIDs route seamlessly across web architectures, directing requests peer-to-peer without central servers. However, DIDs only identify nodes. They lack the mathematical weight to actually prove claimed identity attributes. A TypeScript frontend alone cannot securely compute and verify an identity. Attempting to process verification directly at this layer would eventually expose the user's private payload data to the open network. To secure that payload, we have to dive beneath the network surface, crossing the cryptographic gap into a highly specialized, heavily armored backend. Standard cryptographic backends suffer from a primary vulnerability: memory leaks. Improperly managed memory allocation can accidentally expose private cryptographic keys to other concurrent processes. We implement Rust as our specific engineering solution to prevent this backend key exposure. This demonstrates Rust's ownership model. The compiler ensures each piece of data has a single owner, mathematically preventing buffer overflows. Sensitive user data flows into securely walled-off memory blocks, contrasting legacy architectures that share memory states and risk exposure. Establishing this impenetrable, memory-safe foundation is the technical requirement before computing complex cryptographic proofs. With the memory locked down, we execute the core operation inside the Rust backend, the generation of zero-knowledge proofs, or ZKPs. In a ZKP, readable raw data enters an opaque mathematical function, outputting a unique encrypted verification key. This proves a statement while destroying input visibility. Lacking underlying source material, this guarantees verified privacy, unlike traditional OAuth exchanges, which inherently expose payload properties. By utilizing this engine, the protocol mathematically guarantees that the user's raw private data never leaves their localized, secure device layer. Once the computation is complete, the encrypted ZKP output routes back up from the isolated Rust backend, crossing the gap into the dynamic TypeScript layer. The TypeScript layer receives the raw cryptographic proof and initiates a packaging process to make it functional on the open web. This step encases the ZKP token inside a standardized transportable object known as a verifiable credential, or VC. Armed with the mathematical certainty of the ZKP payload, this verifiable credential acts as the user's portable, cryptographically signed record, ready for global deployment. Pulling back to a full stack view, we can observe the fully assembled two-tier architecture operating in a live global network environment. The process begins with a user node presenting the compiled verifiable credential, routing it directly to a receiving verifier node. Upon receipt, the verifier node independently processes the object, checking the mathematical proof held inside the VC to confirm its validity. Notice the exact routing path. There is no network request reaching back to a centralized identity database. The transaction completes securely, relying on the localized protocol logic held between the two independent peers. TypeScript's dynamic agility orchestrated the network delivery, while Rust's strict security generated the mathematical proof. This localized, trustless transaction proves that the cryptographic gap between web routing and backend security has been closed. This evenly distributed constellation represents the elimination of the centralized authority as a single point of failure in the identity stack. The engineering outcome is a secure, decentralized protocol that protects user privacy by default. Users no longer ask permission to verify who they are. They retain exclusive possession of their identifying data. By replacing central servers with verifiable cryptography, this sovereign architecture enables identity verification to function as a peer-to-peer interaction rather than a centralized service.